Hey, welcome back for lesson 6 in our calculus first unit on limits. I'm pretty excited about today. I get a day off. I don't have to teach anything. You have to do all the work. Nah, I'm just kidding. I'll go over and help you check your work. But that being said, we're starting off this lesson with nothing but practices, so you know what to do. If you haven't already, pause the video. You can work as many as you want. Just pause the video before each time I go over it. But starting here, I'm just going to go over each one of these problems. All right, so if you've made it this far in the video, you are ready for me to go over this question. Now, so for this one here, we can be kind of clever. We can actually factor this as a difference of two squares, but we could also expand it out. So let me show you how I would do it if I factor it. I just think it's kind of a neat thing to do. It becomes x minus 5 times x minus 5 plus 5. So it would probably be better if I used like colors to kind of group it. You see what I'm doing there? That's this part here, okay? And it stays the same. It's a difference of two squares. So I'm using this pattern here. A squared minus b squared is a minus b times a plus b. So I just took the squared off that x minus 5 and made it minus 5 and plus 5. And, what does that do for me? It becomes x minus 10 times x over x, which reduces to just x minus 10. So when we plug in 0, we get negative 10. Now, if you did it a different way, you could have expanded out. So this is the alternate take, as they say, right? Another way to do this, you could expand this out. You get x squared minus 10x plus 25. Please be careful about expanding binomials. You have to multiply these. It's this squared, then this times this doubled, and then the last thing squared over x, and then that's going to give you x squared minus 10x over x, and then I've got an x in each term. I could factor it out, but I can also just divide each one of these terms by x, since it's just an x at the bottom, giving me x minus 10. So the answer is negative 10. Two ways to do it. Two ways to get it right. All right, ready for the next one? If not, pause the video. But I'm just going to keep going. All right, on this one here, let's multiply the top and bottom of this fraction by the denominators that I want to get rid of, 4 plus x and 4. Okay, so this becomes the limit as x approaches 0. The 4 plus x's cancel out, and I'm left with just a 4. Here, the 4's cancel out, and I'm left with 4 plus x. And, I oftentimes just go ahead and distribute that negative, but I'll keep it out for this one here. All right, so then this becomes the limit as x approaches 0 of 4 minus x over x times 4 plus x times 4, which becomes the limit as x approaches 0 of a negative x over x times 4 plus x times 4. And I will reduce to make that a negative 1. So it becomes the limit as x approaches 0 of a negative 1 over 4 plus x times 4. Now I'm going to plug in 0 for x, and I get a negative 1 over 4 times 4 is 16. All right, coming at you now, letter C. Why does that? Okay, letter C. Alrighty, I am going to rationalize the numerator. So I'm going to multiply by the conjugate here, plus 5. And what I do on the top, I got to do on the bottom. So this becomes the limit as x approaches 0 of 25 plus x. Then it's going to be the square root of 25 plus x times 5. Then it'll be a minus 5 times the square root of 25 plus x. Those will cancel out. So it's just going to be a negative 25. And then x times the square root of 25 plus x plus 5. You know, just in case you didn't see how I got from here to here, this becomes the middle step that I left off was the square root of 25 plus x times 5, and then on the inside I have minus 5. That was the outer product here to here. Then the inner product gives me a minus 5 times the same thing. Those are the same thing because it's 5 times that minus 5 times that same thing. They cancel out. Okay? All right. Now what can we do? Well, we can subtract 25 from the tops, right? They combine to just x over x times the square root of 25 plus x plus 5. Then these here can reduce to 1s. And I'm left with the limit as x approaches 0 of 1 over the square root of 25 plus x plus 5. Plugging in 0 for x gives me 1 over the square root of 25 is 5, plus 5 is 10. All right, now we're ready for letter D, right? All right, on this one here, you should factor the denominator and the numerator, actually. So it'll be x minus 5 times x plus 3 on top. This is a sum of two cubes pattern. The sum of two cubes pattern, a cubed plus b cubed, factors as a plus b times a squared minus ab plus b squared. So this will be x plus 3 times square of the x, multiply these two together, but change the sign. I forgot to change the sign. So minus 3x, and then square that last number, plus 9. All right, these reduce to 1. I'm going to go ahead and plug in if you don't mind. So it's negative 3 minus 5 over a negative 3 squared minus 3 times a negative 3 plus 9. So that's a negative 8 over 9 plus 9 plus 9, which is a negative 8 over 27. I want to point something out. Did you notice that when I plugged in this negative 3 here, I used parentheses? You know, I could get away with not using it here and just say negative 3 times negative 3, but you must use parentheses when you plug in a negative number with the squared, even if you know it's supposed to be a positive 9. Because if you write this and then call that positive 9, even if that's what it should have been, this does not equal that. So you've just had an inconsistent intermediary step. That is something we do not want in mathematics, especially not on an AP calculus test. All right, moving on. So, I don't know if you stopped here, but we're now in the practice 6.2. So, if you haven't, go ahead and pause the video and do those. You can do them again one at a time if you want, and we'll check them one at a time. Or you can do all of them, and then we'll check them. It's totally up to you. But regardless, there's the first problem. Pause it if you haven't done it yet. Otherwise, here we go. All right. So this is an unusual one. We've talked about just like directly plugging in and how some things that are nicely behaved, limits that involve functions that are nicely behaved. What I mean by that is definitely no step function, definitely no piecewise defined function. And it's time that you start seeing the absolute value function as a piecewise defined function. The absolute value of x is defined to be negative x if x is less than 0, and positive x if x is greater than or equal to 0. It actually doesn't matter where I put the equal to sign there, because 0 doesn't matter if it's positive or negative. But so you need to realize that this is not a quote unquote well-behaved function. We really need to be careful with what we're doing. We know about this situation here where we have this over this, right? We need to keep that together. So I am gonna use my limit properties, but I'm going to split it up here and then keep the rest of it together. I think we've seen that before, but maybe just once. All right. So if I plug in 2, I can directly evaluate this. This is a left-hand limit, by the way. We're coming from the left because of the little minus there. If I plug in 2, I'll get 6 there. So that's fine. But we need to think about what this is. If I were to draw a sketch of it, we know that x minus 2 over itself is 1 as everywhere, right? So the absolute value of x minus 2 is the same as x minus 2 as long as it evaluates to a positive number. So that's going to be for all values greater than 2, right? So at 2, it's going to, and beyond, it's going to evaluate to 1. At exactly 2, it's undefined because of the divide by 0. And then down here, when x is less than 2, because you have like, you'll have a negative number down here, but a positive number because of the absolute value, we're going to evaluate to negative 1. So if I'm coming from the left, I'm actually going to be going towards negative 1 here on the y value. So this is going to be 6 times a negative 1, making this a negative 6. Okay? Challenging, but those are good, important concepts for you to know. All right, letter B. Okay, so this is the step function now. We know that that's not a well-behaved function, so we're really going to have to use our properties and be careful how we do this. So this is the limit. I'll split this up around the multiplication. As x approaches 2 from the left of 3x times the limit as x approaches 2 from the left of x minus 2 over x minus 2. Again, this one's easy. That's just 6. So let's talk about approaching 2 from the left in this function. Oof, you know, this is a tough one. Let's take our time here. These step functions, when they have this thing down here, always kind of eat my lunch. I don't know about you. All right, so we got something going on at 2, but let's go backwards a little bit and kind of like get the pattern of this function. So I'm going to be looking at this top function here, okay? And I've got when x is 2, you're going to have 0, okay? So that'll be exactly a 0 there, but then everything up till 3 will also be a 0 because it's the greatest integer function. So if I plug in like 2.9, that'll become 0.9, and the greatest integer less than or equal to 0.9 is 0. So it's going to be like that. And then it'll go up to 1. All right, and then here, and then here. Okay? So we know that this top value here, this value here, if I'm going to come from negative 2, I'm going towards negative 2, but from the left, I'm actually approaching the value negative 1. So this numerator is approaching negative 1. Now, the bottom is approaching 0, right? But from where? It's approaching 0, but for values of 2 that for values that are less than 2. So, for example, like 1.99999, when I subtract 2 from that, it's going to be a negative number. So it's approaching 0 but negative. So it's definitely negative, right? So let's think about it. What happens if you divide a number like -1 by a number very close to 0 but negative? Well, I think you can agree that it'll be positive. But do you agree that it's going to be some infinite value? That it's going to be approaching an infinity? That I'm going to be dividing a number close to -1 by a number close to but not exactly 0. If you divide, the negatives will cancel out, and if you divide 1 by a number smaller and smaller and smaller, you get a bigger and bigger number for a result. So this limit is infinity. Okay, so we have another one to do. All right, this is the next one. I didn't skip any today. Okay, so if you haven't, this is a good time to pause the video. If you've already done it, though, we're going to move on. All right, we're going to evaluate the limit as x approaches 5 at the cotangent of pi x over 6. So I'm going to put a 5 in for x, and I'm just going to evaluate and make sure that you always check that first before you start doing a bunch of algebra. Cotangent of pi times 5, I'll just call it 5 pi over 6. All right, so that is cosine over sine. We could find the cosine of each one and the sine of each one. It's also 1 over tangent. It'd be nice if you had your tangents memorized. I'll go ahead and show this as cosine over sine. Remember, tangent is sine over cosine. This is cosine over sine because it's tangent flipped over. All right, the cosine of 5 pi over 6 is 5 pi over 6 is an angle that is in quadrant 2, where the x's are negative and the y's are positive. So cosine is the x value, so we know that this is going to be a negative. A negative what? Well, the cosine of pi over 6 is root 3 over 2. It's very flat, so the x value is very far over, and root 3 over 2 is a bigger number. Over the sine of 5 pi over 6, well, that's just a positive number because it's in quadrant 2 where y's are positive, and it's over 1/2. And they always have the same denominator here, and these just cancel out by multiplying on top and bottom by 2. So the answer is simply a negative root 3. But y'all, it's really going to help for you to learn your tangents, okay? So let's just review tangents for just a second. All right, so the tangent of 0, that one's easy. It's just 0. The tangent of pi over 6, let's come back to that. The tangent of pi over 4, which is in the middle, that's 1 because the sine and cosine is the same. Also, remember, tangent is the slope of that line there, and that's the line y equals x. Then we got pi over 3. Let's come back to that one, okay? And then this one here, what's the slope of a line going straight up? Undefined, right? And that's what tangent is, a slope. So undefined. So I'm going to argue that these three, the tangent of 0, the tangent of any pi over 4, the tangent of pi over 2, those are all pretty easy to remember. It's these pesky, what do we do when it's pi over 6? What is the tangent of pi over 6? Well, the tangent of pi over 6, how many 3's are in 6, right? There's 2 of them, right? 2 3's, 3 plus 3 is 6. And that's how I remember that the tangent is the square root of 3 over 3. Then over here we have pi over 3, right? And how many 3's are in that? Well, there's only 1 3, and so I remember that that's the one that's just a single root 3. And what is cotangent? Cotangent is just tangent flipped over. And flipping it over means the undefined becomes the 0. The 1 stays the same. And root 3 goes here, and root 3 over 3 goes over there. Anyway, I will tell you that when having to solve equations on the AP Calculus test, the tangents and cotangents are really very simple. They like to stick with like equaling 1 or 0, something like that. So really don't worry too much about it. Just, when you get a chance to practice and review your unit circle, do so. That's about all I can say. All right, let's go down to letter B, because that one was done, right? We plugged in and we got a real value. We're done. All right, now if I plug in 0 here, you are not going to get a real value. You're going to get 0 over 0. So, But we know we have that limit as x approaches 0 of sine x over x to our advantage. So let's go for that. So limit as x approaches 0, I have the sine of x over, I'm going to factor out an x, and I'll be left with 5x minus 8. And then I'll use my limit properties here. This becomes the sine of x over x times the limit as x approaches 0 of 1, because there was nothing left on top, over 5x minus 8. We know what this is. The limit as x approaches 0 of sine of x over x is 1. We have that memorized. That's right. I said memorized. All right, now we're going to plug in 0 for x. You get 1 over a negative 8. So our answer is simply negative 1 over 8. I can pull the negative out in front or up on top or leave it on bottom, whatever you prefer. Okay, so on this next one, we have the 5 times the sine of 2x over the sine of 3x. You know, I'm going to prove this limit, okay? But you can skip right to the answer if you remember when you have this sine over sine that it's just going to be 2 over 3 times 5. But I'm going to multiply by 1 over x on top and bottom, and I'm also going to pull out the 5 because that's pointless. It's just going to multiply my answer by 5. So I guess it's not pointless, but I don't need to play with it. I can pull out a constant. And so I'm also going to split this up around the quotient. So this becomes sine of 2x over x. And on bottom, I got the limit as x approaches 0 of the sine of 3x over x. Right? Now, this here, I can do that little fancy maneuvering I did once to prove it. I am not going to go that far. I'm going to hope you remember that when the angles are not the same there, it's just the ratio. So it's 2. So this is 5 times 2. And on bottom, that's 3 over 1, so over 3. So the answer is 10/3. Okay, that's it, y'all. We are quickly coming to the end of our unit on limits. We are going to look at limits at infinity next. And that is super duper important as well. So keep studying hard, keep working hard, and anytime you get a chance to practice, and just keep getting better. Until I see you again, take care.